All right. Thanks for coming, everybody. My name is Jim Box. I'm a data scientist at the SAST Institute, where I've been for the past 8 years. Prior to that, I worked in clinical trials research. So I've been around um, modeling for quite a while. Got a degree in analytics from NC State, where we did a lot of big data study kind of stuff like that. And today, we're going to talk about how we as humans can identify sources of bias in machine learning models. And it's a topic that's really sort of important to me and several of my colleagues here at SAS. So hopefully you find this interesting. To get started, I want to define a couple of terms because depending on who you're talking to, sometimes you hear AI and machine learning sort of referred to interchangeably. So I just want to focus on what we're talking about. From my perspective, artificial intelligence is this idea of the science of training systems to emulate human tasks through learning and automation. And there's a lot of different ways that artificial intelligence can kick in. It can be not very intelligent, something like a phone system where you're putting in numbers and it's responding to the numbers that you typed and sending you to somebody else to ignore your call. Or it can be something that's really sort of well thought out and is really responding to information that it gets on the fly. And you can see that machine learning is one method that sort of powers the artificial intelligence. And inside machine learning, there's deep learning, and we could talk about that, but that's essentially starting to look at pictures and whatnot. There's natural language processing. There's a whole bunch of other things I could focus on there. When I'm talking about machine learning, I'm talking about the idea that systems can learn from data, can identify patterns, and can make decisions with minimal to no human intervention, right? And why this is important and why it's important to talk about bias is machine learning AI systems are really prevalent in all sorts of facets of life, right? They're very big in the financial world where you're looking at who's going to get approved for a loan and at what rate are they going to be approved and what services could be provided to them. In the criminal justice world, machine learning models and AI systems are used to actually help determine the sentence structure for people and whether or not they qualify for parole. So there's a couple of large systems that look into trying to pick recidivism, which is the chances that a person will recommit a crime, and if that model comes up with a high prediction, then that person doesn't get parole. Right? In healthcare, it's who can be admitted to a healthcare management program, or it could be what treatments are you given. We're going to look at some examples a little bit later, specifically in healthcare, because that's my particular field. HR, it can be things like who gets moved up to the next stage of hiring process. We do a lot of models with HR organizations to figure out what employees are at high risk leaving the organization. So there's a lot of places where this impacts you. Some of them are very open about it. Some of the times it's really not very clear that a machine learning model has made a decision. A lot of people are moving towards artificial intelligence and machine learning models to make decisions that are particularly troublesome so they can then blame it on the computer if something bad happens to society. I wasn't discriminating against this person. I was just doing what the model told me to do. There's actually a term for that. It's called math washing. The idea that you can you can blame a hard decision on the math. Right. Recently, we saw this was something published this year in the MIT Technology Review, talking about all the different AI tools that were built to either catch COVID or diagnose it or try to predict who was at high at risk, and not a one of them was really useful. Right. And this isn't surprising, and we're going to talk about some of the reasons why some of the things happened there. But AI is really big. People are really trying to use it. So when we think about the machine learning, again, I'm going to focus on machine learning. There's really three sort of steps in the machine learning world. First is you have some sort of input data. You then apply one or many algorithms to this data, right? And there's always a new algorithm. There's always somebody else working on their PhD thesis. There's always some company trying to come up with another algorithm that can make some sort of decision. And on the output, you wind up with a prediction, the chances this person's going to recommit a crime, a forecast where you might be looking at, what is demand going to be in 3 quarters from now, recommendation, like recommendation engines that we see in, oh, you watch this movie, you might like this movie, decisions. There's all kinds of different outputs that can happen in machine learning. So bias comes into each of these 3 areas, and it shows up in slightly different ways. First off, and I think the most insidious one, and we'll spend quite a bit of time talking through this, is that biased data is going to give biased results. So whatever human biases exist in the training data, and pretty much if the data was collected by humans, there's going to be some bias in there. That's going to have an impact on how this algorithm works and everything goes. On the algorithm side, it's really important to understand that algorithms and models do what you tell them to do, which might not be what you wanted them to do. So you have to be very specific about how you set up a model and what it is you're trying to do. And I'll show you a couple of examples where that went wrong. And finally, on the prediction, forecast, recommendation idea, that if you're exposing a model to data that's not like the data it was trained on, it can give you some really unexpected results, but you won't necessarily know that there's any sort of risk involved with those. Okay, so we're going to delve into each one of these, and let's start with the training data, because I think that's the sort of bedrock concept. The best way to illustrate this is to give you an example. So in about 2015, Amazon decided to undergo an AI project where, they get a lot of resumes for every position that they have open. And they realize, what? Our whole core business is to rank products and to say, if you like this, you'll like that. So why don't we apply that to the resumes that are coming in? So they built this AI system, look through the resumes and use some natural language processing and see everything that's coming in, and then compare that to applicants based on who they'd hired in the past. Okay, so we hired this guy in the past, so we might like this person. And so they actually gave star levels to the CVs that came in, and then they focused on doing the interviews to the 5-star candidates, right? So seems like a pretty sensible thing to do. Amazon's good at ranking things. We got a lot of resumes coming in. Let's let the AI system comb through the first part, right? So I'm giving you a talk on bias. Something went wrong. Here's what went wrong. It immediately started showing bias against women, right? So here was a big problem. Why did it show bias against women? Was there something wrong with the algorithm? No. The training data they used was, let's look at all the resumes we got before of people that we hired. Well, historically, Amazon had really had a strong bias towards hiring men. So the model kind of learned that, we don't really like who we think are women. And let me show you how that played out, because it really is kind of insidious, right? So here's an example. One of my coworkers kind of came up and gave us a chunk of her resume, and let's look at how the Amazon system would look through this, right? So again, it's been trained essentially to lower the rating for women. So the first thing this thing notices is that Elena was part of the women's chess club, right? So there's the word women right on the resume. Also her name itself would have been one of these other things that triggered. So the model was actually degrading her score because it said women's chess in there. Now, to Amazon's credit, they were looking to see what was happening, and they wanted to see how the model worked, and they realized right off the bat that, it's excluding women or people who are easily identified as being women on their CVs. So they adjusted the process a little bit. They told it, ignore if you see the word women, or ignore maybe some of these feminine names, although that can get a little tricky. You don't want to worry about that too much. Or maybe ignore the names altogether, right? But ignore the women's idea. Okay, so that's a good approach. Run the resume through there again, and what happens is it picks up on Smith College. Smith College happens to be an all-women's school, right? So they've never had anybody who came from someplace like Smith College, so it got ignored that way. So there were some sort of secondary indications of assumed gender in here, and I won't even get into the problem of assuming somebody's gender, but there were some secondary indications, like where they went to school. Maybe they went to a school or had a major that didn't have a lot of women in it, right? So they were able to go through and put a second kind of group of don't look at these values in it, and wanted to see how that went. Well, here's where it got really bad, because what the model was also able to do was look at the language in which people use to describe themselves. Look at some of the verbs they use, some of the adjectives, and some of the things they talk about. And they find that communicating effectively was something that women tended to put on resumes more than men. Communicating effectively is always a good skill to have, but the people that they had hired in the past, being men, hadn't highlighted that on their resumes. So it started throwing people out based off the language they were using, right? So the key point here, the key takeaway, is that when you're training a model on biased data, it's going to be really good at applying that bias. It would be even more efficiently applying it than humans, right? If I had stripped off anything that was obvious about gender, you might not have picked up on the language differences, right? So this data was biased, and the model picked up on it and got really good at applying those biases. So when you're doing this process, whether you're the programmer or you're the person who is being presented these results, some of your responsibilities are going to be, all right, tell me about this training data. Where did it come from? How representative is it? Does it cover men and women? Does it cover different racial groups? Does it cover different, whatever types of groups? How did it get labeled? How did we decide what a success was and what wasn't a success? And is there some sort of feedback loop when I'm finding things about this? Right. So it's really important that we sort of think about these things. When I was looking at different examples to use for this, it turns out that one of the very first use cases of using a ranking system with a machine learning sort of model was done in the 60s by the British National Health Service, where they were looking at what doctors to admit to their programs, their training programs. And the first thing that model did, based off the data it had been trained on, was throw away any doctor who came from a country in Africa, right? So this problem has existed, this specific problem has existed for as long as there's been people trying to classify resumes, but it's a very insidious problem across all sorts of things, right? And I should make a note, if you have questions, go ahead and put them in the chat, and at the end, I'll kind of get to them. So if you have any questions that come up, just put a Q in the chat and we'll talk about it later. All right, so that's the training data perspective. The second thing I want you to think about is that models do what you tell them to do, right? And it's very important to understand that. You may think you may assume some nuance that your model is not going to assume. And here's a really good example. And this is a little bit of a constructing example, but these guys wanted to prove a point. So they trained a model to distinguish between a husky and a wolf. So they gave, I think, something like 100 images or so to this system, and label them as this one's a wolf and this one's a husky, and let the model kind of come through and figure out, if it could predict, if given new pictures, if it could predict which ones were wolves and which ones were huskies, right? So they trained the model, they gave it these 6 images and said, all right, go ahead and predict. Is this a wolf or this is a husky? And what you would assume was going on, right, is that, okay, the way that you and I might distinguish between a wolf and a husky is we'd look at the coloring of the animal. We'd look at its sort of the shape of its face. The wolves look like a little bit more triangular in the face and the way their eyes are. Huskies tend to have, blue eyes or black eyes. Maybe the ears are a little bit different, right? The main thing that determined how this model worked and predicted whether or not it was a husky or a wolf, and if we're in the room, I'm sure a few of you have shouted this out, is the snow in the background, right? The model quickly learned that picture of an animal taken outside with snow tended to be a wolf, and so it predicted wolves for anything it saw snow with, right? So the algorithm effectively did what you asked it to do. It found ways to group these animals into either wolves or huskies, and it did it in a way that was fairly accurate, but was not anything that you would have wanted it to do. It did what you told it to do, but not what you wanted it to do, right? And of course, what you could have done here to mitigate that is gone through and taken these images and blurred out the backgrounds, right? And then kind of done a model that way to see what would happen. An example of that in the life sciences, healthcare sort of world is one of the things that we're trying to do a lot is have machines look at images from radiology, MRIs, X-rays, and try to figure out which patients are the most problematic. In this particular case, we're trying to teach this system how to diagnose people who have an enlarged heart, right? So we train the model on labeled images and then applied the images to new images to see how it did. This particular patient we're looking at has the condition, and the model gave it a probability of 75%, right? So it seems like, okay, the model seems to sort of know what it's doing. It did a pretty good job predicting who had the problem and who didn't have the condition. So that's great. So we might think, good, this is a good model. We can move on, let it go through here, have it sort through these images, and maybe the top 25% of these images are people that we look a little bit closer at. Well, one of the things that you can do with looking at how a model and an algorithm looks at an image is to sort of look at a heat map. And the heat map sort of shows you how important each area of this image was in determining how it was going to do the prediction, right? And you'll notice that for the most part, those 3 7s and 3 5s in the middle there are looking at where the heart is. And that's what you sort of expect. And maybe what I would think would happen is it would look at the size of the heart relative to how it can distinguish the sternum, or where its position is in the rib cage, or how far it is from the clavicles. So those are all things that we would sort of expect the thing to spend time on. But what we found interesting was some of the time and some of the weight it put on things that we didn't really think about. And in particular, it was looking at that word in the upper right-hand corner where it says portable. And it was looking at other metadata tags that were in this X-ray that came in the image file that we didn't maybe necessarily even know it was looking at. And specifically on this portable thing, it was taking into account the idea that if this patient was examined by a portable X-ray, it gave a higher probability that this person had the condition that was sick, that was not doing well. Well, if you think about that, the type of people who get a portable X-ray machine are typically the type of people who they don't want to take out of the bed and get them down to X-ray, so they tend to be sicker. So we already knew they were sicker because they got the portable X-ray. So that's not really helpful to determine if they have the enlarged heart condition. This model was also looking at, like I said, some of the other metadata tags, and it quickly learned that images that had been reviewed by these certain radiologists tended to have the condition, right? And the problem there was that these were the radiologists who specialized in this and the ones that would look at most of the cases. So this model was using parts of the image that we did not expect it to be using. And in fact, here's another case. This is a woman who actually has the condition, but you'll notice in the upper right-hand corner, she didn't have the word portable. So the model actually lowered the probability she had the condition because it didn't say portable there, right? So it's a real deal where this model was looking at things that we did not expect it to look at. And that's a real problem anytime you're doing a model that's very complex, right? It's really hard to understand what a neural network is actually doing and where it's spending its time. But a model like this would give you results and it would look like, oh, it was right 90% of the time. This must be a really good model. Well, you don't know that if you don't understand what's going on, right? Models are lazy. They will find the easiest way to break things up into different groups, but they're effective, right? They don't care about context unless you specifically instructed them. Right? This model had no idea that it should only be looking at the heart and it shouldn't be looking at some of these other things, because we just said, here's a bunch of images, you figure it out, right? So think about when you're thinking about models like this, especially a black box model, you need to think about it like a particularly tricky 4-year-old, right? You go into her room and there's clothes all over the floor. You tell her she can't have any dessert until there's no more clothes on her floor. And so what you might be thinking is that means she's going to pick them up and put them in the hamper, or if they're clean, put them in the drawers. But what she really did is just jam them all underneath the bed. Well, she did what you told her to do. You got the clothes off the floor, but that's not what you meant for her to do. And that's how you have to think about how these models work. It looks like they know what they're doing, but there's no particular reason to think that unless you look at it. One of the most important things to do, especially when it's a black box model, is try to understand, why did the model make this specific prediction for this specific case, right? You gave me a 95% chance of having a condition. Why? What were the variables that were most important? And those variables need to make sense. And we're going to look at an example, sort of a live example here in a couple of minutes, where I'll show you that, right? So it's really important to understand what's being used to make the predictions and what exactly the model was set up to do. And part of our responsibility if we're the data scientists is to document this, right? Talk specifically about what the model was supposed to be doing and what it was supposed to be looking at, and talk specifically about how we checked to make sure that it was doing things in a sensible sort of way. And the third example I want to give you is this idea that models might not perform well on novel data, right? So if you train a model on a certain type of data, and then you try to apply that model to another type of data, you could run into some really unexpected results, right? So they should really only be applied to data that's similar to the trained data. And then here's the problem. It's going to return a prediction on this novel data, and it's going to appear to be trustworthy, but it might be garbage, right? So it's really important to understand that. And again, let's go back to the 3 or 4 year olds, the way that you teach them how to understand what animals look like, right? And this is how you teach a machine learning model: is you show it a whole bunch of pictures of things that are labeled dogs and things that are labeled bunnies. And it might look at these dogs and start to realize that, okay, dogs sort of sit the same way, and their ears hang down and their tongues sort of hang out. And, as you're pointing your kid at these pictures, dog, the bunny, you got a side view, you got ears sticking up. She can start to figure out, based on the types of pictures that you're showing her, oh yeah, these are dogs, these are bunnies. I get it. And then you show her something like this thing, right? What the heck is this? Is this a dog? Is it a bunny? When I was doing this presentation for my internal team, one of them actually had his 3-year-old sitting on her lap, and the 3-year-old said that she thought this was an elephant, right? So, it's got the ears like a bunny, it's sort of sitting like a dog. I don't really know what it is. And that's the problem. The model's going to come out and say unequivocally, this is a dog. But are we really sure? Do we know why it made that decision? That's a silly example. Here's one that's more problematic, right? So the National Health Service has this really big data bank of genomic data that they use to compare somebody's genomic profile and do some things to look at predictions, to look at things like risks that they might have. This specifically is a risk of schizophrenia. And what they found was that this genetic test was predicting schizophrenia at a risk that was 10 times higher with people with African ancestry than those with Northern European ancestry. This had nothing to do with people from Africa being more susceptible to schizophrenia. The problem here was the data bank was almost entirely made out of white Northern Europeans. And so when it had different genetic markers that it was exposed to in the model, it kind of scored them towards having schizophrenia, right? So this is a really big problem. And again, one of the things that makes this really hard to detect is you don't really tell from the model. It's not going to tell you, well, I'm not sure, but I think it's this. It's going to say, with 92% accuracy, I say this, right? So our responsibility here is to sort of question the application, right? Is the data similar to what the model was trained on? So you need to understand what the model was trained on. The different groups or different population subgroups in my predictions get different results, and I'm going to show you how we look at that in a minute. And then is there a human feedback loop that allows for retraining the model? There's a really popular image repository that people use to train models, and one of the things is one group was trying to train a model to detect if a person was wearing a costume or not, right? And so it had hundreds of thousands of images, and it would determine, is this a costume? Is this normal dress? When fed a picture of a woman in a traditional Indian sari kind of attire, it predicted that she was wearing a costume, right? And the reason it did that is that this image database had in it only 4% of the images were of people of Indian descent, right? And about 18% of the world is of Indian descent. So this woman was wearing clothing that for her represented Thursday, but for the images that were trained on the models that are trained on images of mostly white people, it kind of told us it was a costume, right? So it's really problematic. So the summary, where do these biases come from, right? So like children, models pick up patterns in the data we're not explicitly trying to teach them, right? It's going to find any way of dividing these things, this data, into the groups that we're searching for. There's a lack of awareness, especially by data scientists in the US and Western Europe, about how these historical societal biases may be present in data modeling. We don't think about this, right? Because we haven't had to think about it. A lot of times, the people who are data scientists or statisticians haven't been the people who have been subjected to some of these societal biases. So we can tend to not be aware of them, right? And these biases are in how we collect data, the types of problems we're trying to solve on, what kind of data we're using to train the models, how we assess the accuracy, and how we present the results. So it's really incumbent on us as data scientists, data practitioners, to be aware of this and to be thinking about it. And let's do a little bit of a demonstration. So my demonstration here, I'm going to show you a couple things where we looked at a model predicting whether patients admitting to the ICU were previously diagnosed as diabetic, right? So these are patients who have come into the ICU where we can't ask them the question. They're not conscious, they're not aware, and they can't tell us whether or not they have diabetes. It's really important to know this because that might inform the way you do some treatments. And if you don't know in these first 24 hours while this person's in the ICU whether or not they are diabetic, you might give them a poor treatment, right? So we build this model, and then we get some information coming in that the model that we built didn't perform well for some groups. So let me share this other screen. Where is it? I'll just share my whole screen. Let's go into this and return my application here. So we build a model to predict how people would, if people were diabetic, based off of any parameters that we could review in the first 24 hours of when they came in the door. Right. All right. So hang on just a second. This was all loaded up before I started. And I'm just going to show you a couple of things here, and then I'll stop for questions. Right. So one of the first things we want to do, right? I have about 130,000 people in the data set that I trained this on. Right. I had about 54% men, 45% women. Had about 21% of people that I trained this model on were actually diabetic. And you can see that it was mostly white people that I looked at. Right. So the first thing I might want to do is say, all right, I've trained my model on data with these sorts of parameters. Let me look across the country and see how good was I at coming up with a population that matched the world, right? Or the world in this case is the United States. We got this data from hospitals across the United States, so it wasn't any one particular state. You can see that what we find off the bat is that diabetes prevalence is closer to 16%, but in our sample it was 21%. Might not be a problem. We have a little bit more diabetics than in general. That might make sense for the types of people that show up in the ICU. You see the gender, it's actually 50-50 in the whole population. I had it at 54-46, so that might be a problem. And then you can look at the sort of ethnic breakdowns. And the one that sort of jumps out to me is I have very undercut the Hispanics, right? I only have 3.8% Hispanic people in my population, but if you look at all the people who have diabetics, it's about 10% in the Hispanic population. The other populations are pretty close, right? So one of the things that we can do is look at, and I don't know how much training you have on some of these things, but we can look at how the model performs on these different sorts of groups, right? So we'll do an AUC parity, right, where that's area underneath the curve. And what you're hoping is that the predictions under the curve, the area under the curve, the predictions is about the same for men and women. And in this case, it kind of was, right? This number, we want it as close to 0 as possible. It's pretty close to 0. The equalized odds, where we look at the difference between false positives and true positives, kind of was pretty low too. You look at the biggest number difference between the true positives and the false positives, that was pretty low. So even though our genders were a little imbalanced, the model seems to not really take that into account too much. So we're probably fine with the sort of gender balance that we have. We might want to go and look at race and ethnicity. And in here, we're going to see some more drastic sort of differences, right? So the area under the curve for white people is very different than the area under the curve for Asian people. Is this number really bad? 0.07? It's higher than I would like. Is it a real problem? Maybe. What should we do about it? Anytime you're looking at population studies like this, where the people that you have in your population don't match the population as a whole, one of the things you might do is oversample or undersample some of the population. So we try to get it to about the right level. And you can see that we had a real problem with the true positive rates and the false positive rates. So we have something wrong with the way that we're dealing with folks of an Asian descent. Again, Asian race, some of the race categories are stretches, and we won't get into the problematic thing about there, but we're definitely having a different experience in this model with Asian people than we are with other folks. So that's something to sort of explore and try to understand. The last thing I want to leave you on is one thing that we will frequently do when we're doing models is we will exclude some things that we don't want to be taken into account. For example, when you're doing a lot of financial models, you're not allowed to take things like race or ethnicity into account when you're trying to use a model to predict whether or not this person's going to default on a loan, and that might go ahead and drive the interest rates and the probability that you give them the loan, right? So there are times when you're not allowed to use specific variables based off of regulatory issues, or there might be times when you don't want to. One of the things that's important to explore when you do that is, all right, I can't use race in this particular model. Do I have other variables in there that are sort of proxies for race? And that's what we looked at over here. And what we wanted to do is say, okay, let's throw away the diabetics are not in here and just look at all the data we have collected on people and see, based off these variables, can I predict who are African Americans? Remember, African Americans were about 11% of my population. So at random, a person taken at random should have 11% chance of being from that racial group. But I found some variables that were very predictive of race. And you look at the top three, two of them are ID variables. So it's what ICU they were in and what hospital they were in. Well, what hospital you're going to, especially if you're going to an emergency room, is very indicative of where you live. Your zip code is very predictive of what your race is. And so that's the problem we had there, is that, we're essentially telling it where these people live, what neighborhoods they live in. So that was doing something that was being predictive of whether or not they were African American. But I want to draw your attention to this, and this will be my closing point, right? One of the things that was highly predictive of ethnicity was oxygen saturation, right? So we're all familiar with oxygen saturation because we're living in the time of COVID right now. And what this is saying is that people with a higher oxygen saturation, we're getting a higher prediction of being African American. And so when you come across things like that, you want to think, does that make any sense? Why is that going on? And if you do research, and one of the things that we learned early on with COVID is the problem here is that this oxygen saturation is being measured by something called a pulse oximeter, right? And so you've all seen these. Maybe you've had it done where they clamp that thing on your finger and it gives you a reading. And what that's doing is it's shining light through your finger and looking at how it sort of refracts and sort of the coloring of the blood, and is using that to figure out the oxygen level. And what has happened is that when these pulse oximeters were created, they were sort of calibrated for people with light skin. So what happens is if you have dark skin or even dark fingernail polish, the pulse oximeter will give you a higher reading than is actually your blood oxygen saturation, right? And that became a real problem early on in COVID. And one of the reasons why the African American population was having worse outcomes is because when they clamped this pulse oximeter on a person, they got an artificially high blood oxygen level. And so they weren't aware that people were in distress until they got their numbers fell even more. Right. And so this is sort of a known problem. They're doing some work on these pulse oximeters. Sometimes they'll turn the direction of when they put on their hand to get to the sort of lighter skin that tends to be on the fingers. But this is something you wouldn't necessarily have had any idea was going on in your model, right? You wouldn't have any idea that I was doing something that was predicting ethnicity. I can sort of understand the ICU and the hospitals, but that pulse oximetry was something that really sort of came up, right? So that's my kind of that's my presentation. We've got a real problem with the way that biases can show up when we're doing machine learning. One of the big challenges here is the idea that we are easy to be unaware of these sorts of problems. Let's see. I would recommend, if you've got access to Netflix, there's a really cool documentary out there called Coded Bias that talks about this sort of stuff and gives some really good examples and kind of goes through and let you see that. There's a lot of different books that talk about this sort of thing. And it's really sort of a big deal. So I'm going to look and see what's in the chat. And if you have questions that you haven't put in the chat, you can go ahead and come off and off mute and ask a question. Somebody asks Devin asks if there are regulatory requirements for documenting models or how they work. There aren't regulatory requirements yet, right? There are some regulations coming into play about how machine learning works and what's going on that are coming out of the European Union, which typically tends to be the place where privacy and regulatory sort of things come into place, where they're going to start talking about this, going to start pushing it. But right now, there's no real regulation on that. Microsoft has come up with an example of something they call a model scorecard that kind of walks you through the sorts of things that you want to be able to put when you're documenting a model. And a lot of it goes along where the data came from, how it was labeled, like I was talking about earlier. So there are some company examples that are doing things like that, but it's really important to sort of think about that in there. Bias is, Merck asks, bias is always a function of inductive reasoning, so would a human-in-the-loop best practice to review and refine bias outcomes from AI systems? So I think we answered that a little bit by looking at subgroups and seeing, does this model treat all populations the same? And it's really important, especially when you get to these black box models that are just going to give you results, is to understand, why did it make this prediction for this observation, right? And a good system should be able to tell you that, right? You saw the breakdowns in what I showed you. It said, here's why we think this person was African American. Here were the 3 or 4 variables that were most important. Mason, go ahead.
Yeah, thank you. So I just want to try to ask, how do we know when something is an actual bias in the model or whatever other system that we're using versus just some other artifact of just how some other factor just we haven't taken account of, how people either behave or some other factor, like you mentioned about how it's I've seen it several different areas at this point, dark colors absorb more light, and that's an issue for dark skinned people, whether it's face recognition, whether it's kind of the little sink dispenser things with the motion sensor. It uses a light thing where light absorbs it more, so they couldn't actually dispense soap. It's okay, this pops up in a lot of areas. But one of the ones that I'm kind of more interested in here is that I've seen this in a few other places as well, and in a hospital setting, that the average, the median Latino age is 15 years younger than the average white age. And it seems like that would probably explain most, explain most of the difference in the data that you showed and some data that I've seen when people were asking, oh, how come only 2% of the people in the cardiac ward are Latino for our hospital, while the population in the area is 10% of the population. Well, you have to. It turned out they were 20 years younger.
And the answer is you have to look for that sort of stuff, right? And that's the problem, is you can't it doesn't passively come to you. So we had to look and see, are there any kind of things that were predicting race, to see that the pulse oximetry was weird and then had to do some research to understand what was going on there. You'd have to do the same sort of thing to look at what is the population breakdown, what are my demographics breakdown. Oh, my demographics for Hispanic people are very different than other people. Maybe what I do then is do a segmented model where I do a different model for people of that demographic group versus other demographic groups and apply different models to different people as they come in. That might be a sort of a solution. But the whole point here is you have to look for this stuff. And that's kind of my whole thing. I wish I could come up with a color for a ribbon for awareness of this bias. Because again, especially for those of us who are white people, we haven't been problematically, harmed by some of the stuff. So we didn't even think about it. So a lot of it is just really understanding this is a real problem. We can make it much worse with making machine learning and AI sort of systems in place if we're not careful about it. You brought up the facial recognition. The whole point of that coded bias is the woman who the documentary is about was she was an ML scientist, an AI scientist at MIT, doing things with facial recognition, and she noticed that one of the commercial off-the-shelf facial recognition things didn't recognize her face because she's African American, but she happened to have a mask sitting next to her thing, like an artistic, thing, and it was a white porcelain mask, and she put that on, and that thing recognized her right away. Right. So what happened there? Well, it was how the model was trained and what kind of faces it was trained to look for. Right. Twitter had this exact same problem. They had put in this sort of AI way to automatically crop images, and it was cropping out all the black people because they didn't train it very well. To their credit, they realized, you know what, this isn't something AI should be doing, and they went ahead and undid the AI thing and just told people, go ahead and crop these things yourselves. AI is not the answer for everything, right? And we've got one last question in here. I got 1 minute left. Nina says, it feels like both government and industry are moving forward with ML-driven products, but at a pace that hugely outpaces the discussion of bias. Absolutely. Any suggestions on how to push forward adoption of bias testing or bias awareness at the same pace as other development in ML? I'm seeing more and more people giving talks like this. I see more and more articles on places like LinkedIn. I've got a lot of friends that went through the same sort of program I am that are sort of voicing these concerns. And this is where I think it's incumbent on those of us who are practitioners of this science to be getting people to pump the brakes on here, right? We really need to make sure that we're sort of putting that forward as part of our responsibility. I give this same talk to doctors, right, and tell them it's part of their responsibility to question these results and make sure they understand what's kind of going on and going on here. I am seeing this happen in this last question with more of showing up in curriculums, right? I'm seeing different curriculums bringing this concept up, either in seminars or putting things in actual training practices. So it is becoming more popular. But our biggest problem, right, is that more and more tools are just automatically doing AI and ML stuff. And if they're not having baked in discussions and thoughts about how biases might be present, that's a real problem. Some of the software I'm seeing actually tries to do that. We're trying to do that at SAS to be a little bit more open about how we can explore these sort of things. We actually made this whole group of people at SAS that are going to drive how we develop our products to look at this. It's something that a lot of the bigger companies are doing. And with that, I'm out of time. I know we need to set this room up for the next folks. So I thank you all for your attention. I hope you're enjoying the conference. Again, my name is Jim Box, B-O-X. You can find me on LinkedIn pretty easily if you want to connect. And good luck and thanks for your attention.